sorry to bring the cold weather back. So we boarded Sadie, and it was okay because when we got there, we paid, and the lady took her bag. She's like, "Come on, Sadie," and so Sadie went with her and never even looked back at me. And so at that point, I was like, "Whatever, Sadie." Right back at you. And so it was actually not that hard. So we went to the wedding, and my wife wore a dress, and I didn't wear, like a wool suit or anything. And so it was, we decided to walk to the wedding from our hotel because, booze and driving and all that stuff, you don't do it. And we didn't actually end up drinking that much, but it was like 20 degrees on the walk back. So I don't miss that aspect of Michigan, and I was a little sad when I got back here, and it was also still pretty cold. So, oh well. All right, so let's see. Our song of the day was 1 week. Why is it 1 week? Yeah, it's just 1 week. Okay. Oh yeah. So we had a homework due on Friday. We have one due this upcoming Friday. Office hours. You'll have a chance to meet with me every day this week, basically. I have an office hour, and then we have workshop Wednesday, as well as we are going to do the workshop on Easter Sunday. So I'll be here ready to celebrate. Yeah.
Is there a way that you can do like a podcast-style workshop for Easter because we're with our families?
Yeah, my goal on last Wednesday's workshop was to record it, but we were in Millington and they don't have the software, and so I couldn't record it in that case.
I want to go home with my family, but then I also want to.
Yeah, no, we're in 1127 this Sunday, so I'll definitely record it the same way we've been doing it. Yeah. Okay. So let's see. Let's go ahead. Let's quickly look back and think about what we've been talking about. So we ended up on Friday talking about, we introduced the second type of mechanism, which is the Halonian mechanism. So we're no longer going through a carbocation, so that's good because we have better stereoselectivity. So we have anti-stereo selectivity compared to no stereo selectivity with carbocations. So furthermore, we're not going through a carbocation, so we can't have any 1-2 shifts. So that even further simplifies our products. We saw that the regiochemistry remained Markovnikov, and that's because this carbon has a little more positive charge on it than this carbon, and so ultimately the nucleophile is attracted to the top carbon a little bit more, and so we are still going through a Markovnikov type addition. But we have to go through, so when our nucleophile adds, we end up having to break the bond right here, which we're showing going back to the electrophile, and so the only way that can take place, the only way we can displace something is through a backside attack, and so it has to approach 180 degrees from our wedged electrophile, and so we end up with our nucleophile on a dash and vice versa. So that's how we end up with the anti-stereochemistry in this case. All right, so we'll go right into Roman numeral 6. And so this is going to be basically all of our halonium type mechanisms. So we'll say just X plus reactions and call that good for our titles. All right, so this is, I believe, going to be reaction number 3. And so we're going to refer to this reaction as a halogenation. And so in a halogenation, we'll start with our trusty starting material, our cyclopentene that we've been using so much of. And so with our cyclopentene, in this case, we're going to use one of 2 types of halogens to react with it. So it's either going to be Br2 or Cl2. In this case, we'll use Br2. Now, when we look at bromine, is bromine a polar molecule? It's not, but bromine's pretty far down the periodic table, right? It's at 35, so that means we're getting to a pretty big-sized atoms. And so because they're so big, it means they're also relatively easily polarizable. So it's not a polar bond, but these electrons are taking up more and more space. And so at any given moment, we might find that we have a partial negative on one bromine versus a partial positive on the other bromine. So it's not nearly as strong as having a dipole, but we can have some momentary polarity in our molecule. And so what we show is our electrons, and we always start our arrows with electrons. Please do not ever start an arrow with something other than electrons. All right, so we draw it to our slightly positively charged bromine, and so at the same time, we kick the other bromine off, just as if this were HBr. We're following a very similar type mechanism. But what's different in this case? What extra arrow do we draw? So we have lone pairs now on our electrophile, which is this bromine. And so instead of forming a carbocation, instead of leaving one of these carbons electron deficient, what we want to do is essentially stabilize it with electron density from the bromine. And so where do we start our arrow? At electrons, in this case the electrons of the bromine. And so we'll draw it right back into the, in this case, the tertiary carbocation, or tertiary carbon, I should say. All right, so in doing so, what we end up with is going to be an intermediate that looks like this. And since we have, since this reaction is basically, we're doing these two steps at the same time, right? We're showing that we're drawing this bottom arrow at one time, and then drawing this top arrow at the same time. And because it's happening all at the same time, we have to add to the same face of our alkene, right? So what we end up with is if we approach from the front face, we're going to have our bromine on two wedges. So that'll look like this. So now we've got our three-membered ring, which is so characteristic of this mechanism. Of course, it can also approach from the back face, and so we don't have to draw out that intermediate. What we could just say is what? Yeah, we could just say plus an enantiomer, and I know exactly what you mean. It's the same exact thing, except we're going to flip the chiral centers such that the bromines are going back on dashes and the methyl is on a wedge. All right, so we've also got Br minus floating around in solution, and so that's going to act as a nucleophile. And so which carbon is it going to attack? Is it going to attack the top carbon or the bottom carbon? Which carbon has slightly more positive charge on it? Which would be a more stable carbocation, tertiary or secondary? Tertiary, and because of that, that's going to be the carbon with a little more partial positive on it. So we know we've got partial positive up top, which puts a partial negative on the bottom. And so when we attack with our bromine, we're always going to attack that top carbon, so the more substituted carbon in this case. All right, and so in doing so, our bromine, is it going to have to approach from the front or from the back, or does it even matter? It has to approach from the back, right? It has to approach from the back side of the bromine that it is displacing. And so the bond that we're breaking is this bond right here, and so we know that that bond, since it's breaking, the back side of that bond is going to be on the other side, so on the back face. And so when we draw our product, that second bromine that has come in, is that going to be on a wedge or on a dash? Has it approached from the front or the back? How do we indicate something on the back side? It's a dash. So our bromine here is now on a dash. The methyl has been pushed to the front because of that approaching bromine. And so what about the bottom bond? Is that going to be on a wedge or a dash? It's still on a wedge. We haven't done any chemistry there. Nothing has changed, and so we keep that on a wedge. All right, is that an example of syn or anti-addition? That's anti-addition, right? Because the two things that we've added, the two bromines, they're now on opposite sides. And so this is going to be an example of anti-addition. And that's how all of the polonium mechanisms ultimately go. All right. Is this the only product that will form?
No, it's not.
Yeah, we've also got plus enantiomer, right? Because we have the enantiomer of this intermediate. And so let's go ahead and draw that out just so we're clear on what that looks like. So the stereocenters are reversed, so our methyl is now on a wedge. Our bromines are on a dash. And so in this case, when our bromine comes in and attacks, it attacks the same carbon. But now what is the backside? The backside of this breaking carbon-bromine bond, is that going to be the front or the back? It's now the front, right? Because the bromine bond is going back on a dash. And so when we draw our product, the new carbon-bromine bond that is formed, is that going to be on a wedge or a dash? Well, this bromine, did it attack from the front or the back? From the front, so how do we show that stereochemistry? As a wedge, yeah. So now our bromine here is on a wedge, which has pushed back our methyl. And so the other bromine is still on a dash because we didn't do anything to that position. Okay, so let's go ahead and add that to our table. So this is reaction number 3, halogenation. And so the nucleophile, the electrophile in this case is just some halogen. And then the electrophile is again some halogen. So we'll use X to show those halogens. the two reagents that we'll see used to do this reaction, we're either going to see Br2 or Cl2. So you don't see it with fluorine or iodine, but you do see it with bromine and chlorine. And so anytime you see a pi bond treated with either molecular bromine or molecular chlorine, you know that we're going to go through this halogenation mechanism. All right, what about the regioselectivity here? Well, if we just think about the final product, is there any difference between the electrophile and the nucleophile? There's not, right? So we don't really even see any regiochemistry because we end up with the same two things that we're connecting to both the top carbon and the bottom carbon. So in this case, we would say none. Mechanistically, it's following our Markov-Makov pathway, but at the end, if you just have the product, there's no way to distinguish which bromine really added, and so we'll just say none. It's not really important. Stereochemistry, what would we call it? It's anti, right? So it's anti because of the mechanism that it goes through, and of course that mechanism is the halonium mechanism. So X plus, or our three-membered ring with the X plus. Same thing. All right. So next up, we'll skip ahead right to number 4. So number 4, we're going to call the halohydrin reaction. All right, so the first part is halo. What does that sound like? Halogen, and that's exactly what it is. What about the hydrin part? It sounds a little like hydrate to me, and so what that's going to be is essentially the addition of water, and so we end up with an alcohol. So let's see how this reaction would work. We'll use chlorine in this case, so start with our trusty cyclopentene. So the reagent we're going to react it with is going to be this right here. So we've got a chlorine, and then connected to that chlorine is a hydroxyl group. So between the chlorine and the oxygen, which is more electronegative? Yeah, and so oxygen, they come in on the Pauling scale very similarly, but it turns out that oxygen is almost in all cases going to be more electronegative than chlorine. And so what we have is a partial negative on that oxygen, and that's just the nature of oxygen. It's incredibly electronegative. So that means we're going to have a slight partial positive charge on the chlorine. And so that makes the chlorine our electrophile, since it has that slight partial positive charge. So when we start our mechanism, where are we going to start? Well, at electrons, right? We always start our arrows at electrons. And so furthermore, we always start them with the electrons of the pi bond. That's pretty much happened every time we've done one of these reactions. So where will we end that arrow? At the chlorine. And so similar to above, we basically lose our OH. It gets kicked off. And so what we end up with is some hydroxide in solution. But we don't want to form a carbocation, and so the way that we can avoid forming a carbocation is we're going to use one of the lone pairs on the chlorine to come back and essentially form our three-membered ring. So what we'll end up with is an intermediate that looks like this. Now this has to be on the same side, right? Because all these arrows are going on at one time, and so if a step's going on at one time, this entire molecule, this ClOH, has to approach our double bond either from the top side or from the bottom side, or I guess from our perspective, the front face or the back face. So we'll draw what would result if it approaches from the front face. So we'll have our chlorine on a wedge, and then again our chlorine on a wedge. So that's with a positive charge. Could it approach from the back face? Sure, and so in addition to this, we say we've got this intermediate plus it's an enantiomer. And in most of the cases of these reactions we're going to find that we end up with plus an enantiomer. And that's just because we've got a planar double bond, and so we can approach that planar double bond either from the top side or from the bottom side, and that leads to two products almost invariably. All right, so also in solution, we've got our hydroxide. And so we've seen that water can be a pretty good nucleophile. Do you think hydroxide's a pretty good nucleophile? Well, we've basically taken water and we've put even more electron density on there, right? And so do you think that oxygen would be pretty happy if it could use one of its lone pairs to donate into something? Yeah, absolutely. And so that's what happens. So it's going to donate into one of those carbons. Is it going to be the top carbon or the bottom carbon? Why the top? is tertiary, right? And so it would be a more stable carbocation. So that we've seen that species in equilibrium contributes a little bit more. And so when we add into that top carbon, is it going to attack from the front face or from the back face? Definitely the back face, because the chlorine carbon bond that we're breaking is on the front, so we have to undergo our backside attack. And so if we undergo a backside attack, is our hydroxyl group going to end up on a wedge or a dash? Definitely on a dash, right? Because it's got to approach from behind the molecule. And so in that case, we'll end up with our OH on a dash, which pushes our methyl group forward onto a wedge. And then, of course, our chlorine on the bottom has not undergone any type of change whatsoever, so it's still on a wedge. Is this an anti or syn addition? It's anti, right? Because our chlorine and our hydroxyl group are on opposite sides. And does that make sense for a halonium type mechanism? Yeah, that's what we expect. We expect to just see the anti-product in this case. Is this the only product we would form? No, we'd also form the enantiomer. So it would be this product plus enantiomer. All right, so let's go ahead and add this guy into our table. This will be reaction number 4. It's the halohydrin reaction. What is our electric? Yeah.
Why is it again that in the intermediate step you draw two bonds to the chlorine?
Right here?
Yeah.
It's just more stable that way. So essentially, with our carbocation mechanisms, we have to go through a carbocation because our electrophile is a hydrogen, right? It doesn't have lone pairs that it can contribute back into that carbocation. But if we have a big bulky halogen in place of our hydrogen, well, what we have is essentially, instead of forming a carbocation, what we can do is take one of those lone pairs and just form a new bond. And so by doing so, we have a closed shell intermediate. And so the closed shell intermediate, this thing right here, is just more stable than a carbocation. So this is going to be the leading contribution into that intermediate. Good question. All right, so what is our electrophile in a halohydrin reaction? Is it the halogen, or do we end up with the hydroxyl group as the electrophile? It's the halogen, and so we'll say it's minus X. So that means our nucleophile, or what we end up with as the addition of our nucleophile, is going to be the OH group. All right, so the reagents that you'll see used to undergo this reaction, you can have ClOH, you can have BrOH, and then there's a couple of different possibilities in addition to these. So you could have just Cl2 mixed with water, or you could have Br2 also mixed with water. And I'll run through that mechanism so that we can see that, in fact, we do get the same product, and it does go through a very similar mechanism. All right, the regioselectivity, what would we call it? Do we add our electrophile to the less substituted carbon? All right, so this is our electrophile. Does it end up on the secondary carbon? Yeah, it does over here, right? So this is just a Markovnikov addition. And remember, we're only going to see one example that is not a Markovnikov addition. What about the stereoselectivity, syn or anti? It's anti. So it is a halonium type mechanism. So we can see between 3 and 4, they do have the same stereochemistry, and if the electrophile and nucleophile were different in this step, we would see Markovnikov, but because they're not, we don't really see any. All right, so let's talk about the Cl2H2O mixture of things. So let's see. It's going to be a very similar type mechanism, and so we're reacting with, we use bromine here. So Br2 and H2O. Now, have we already seen a reaction where we have a double bond or an alkene reacting with molecular bromine? Yeah, right, so reaction number 3 was essentially this same exact thing without the water. And so we know how this is going to start. It's going to start just like reaction number 3 did. So, say, just like number 3. So what we'll do is we'll draw to our bromine. Our bromine, of course, has lone pairs. So what we end up with is the same halonium intermediate plus its enantiomer. Alright, so what have we got left in solution? We have Br minus, and we have H2O. And so, we can do one of two things. We can either add in our Br minus to our halonium intermediate, or we could add in water. Which do you think is going to be? Why water? What did we say last time about the nucleophilicity between water versus a halogen? So we said that water is more nucleophilic. So you can ask yourself the reason, all right, why is that? Why is water more nucleophilic than bromide? And so what we find is that nucleophilicity is very similar to basicity, right? Because in both cases, we're donating electrons. And so what we can say, we'll say nucleophilicity comparable to basicity. And so let's compare the basicity of bromine and water. So if we had our bromide and we have H2O, remember thinking back to our acid-base table, we don't have numbers for basicity. We have pKa, right, which is a measure of acidity. And so what we can do is we compare the acidities of these conjugates. And so the conjugates would be, I guess we should draw this as an equilibrium. All right, so what's the conjugate acid of Br minus? HBr. What's the conjugate acid of water? Yeah, that's H3O. And so which is a stronger acid, HBr or H3O? It's HBr. So HBr's pKa is right around minus 7 or 9, or I don't know. It's minus 7, 8, 9, 10, something like that. Really, really, really strong acid. The pKa of H3O plus is right around minus 1.7. And so we see here that HBr is the stronger acid. So knowing what we know about the inverse trends between acidity and basicity, well, which would be the stronger base, bromide or water? Definitely water, right? And so because of HBr being the stronger acid, that means this will be the stronger base. And so if it's also the stronger base, it's also the stronger nucleophile. And so ultimately, that's the reason that we see water be so much more nucleophilic than the conjugates of these strong acids like HBr. It's just because this is going to be a weaker base than water, and so also a weaker nucleophile. Okay, so back up here, what we're going to see react is going to be water and not bromide. So our water adds into our top carbon. So it also adds into the top carbon from the back face, because that's the backside attack as our carbon-bromide bond. So what we'd end up with is going to be our OH2 on a wedge or a dash. Yeah, it's approaching from the back, so it's going to be on a dash. So that pushes our methyl to the front, and our bromide, or our bromine, is still on a wedge here. However, we've still got a charged oxygen, right? So in doing so, by adding water to this thing, we're ultimately transferring the positive charge of the carbocat, or of the halonium right here, to the oxygen there. And so we always want to end up at a neutral product. And so how do we do that? Very similar to when we did the acid-catalyzed hydration, we're just going to deprotonate. And so you can use any base you like. If you want to use just a generic B, that's perfectly fine when drawing mechanisms. And so you would just deprotonate. By deprotonating, we end up with our OH, our methyl, and our bromine there. And so essentially what we find is that's the same thing as if we had added Br, OH, and the mechanism that I showed you previously. All right, so either of those things are perfectly fine for doing the halohydrin reaction. Plus an anti. Is that a syn or an anti-addition? It's still anti, right? Because our bromine and our hydroxyl group have been added on opposite sides. So we still have our anti-addition product. All right, so let's do one more type 2 mechanism. And so this is going to be the oxymercuration reduction mechanism. Sounds awesome, right? All right, so this is my numbering is different. Is this reaction number 5? Yeah, okay. So this is going to be reaction number 5. And so in the oxymercuration reduction reaction, we're going to see our first example of, I guess, what is a 2-step reaction. So what we have sometimes is we're going to find there are cases. So everything thus far, we've been going through intermediates like haloniums or carbocations, and they're not very stable. All right, but sometimes you can end up with a stable intermediate that is not ultimately your end goal. And so what we have to do is to get from that stable intermediate to our end goal, and we'll often just call that a workup step. We'll often add either acid or base or an oxidizing reagent, reducing agent. And so essentially, we don't worry about the mechanism. It's just going to convert that intermediate to our final product. And so in this case, the oxymercuration, we'll go ahead and write that down. It's the oxymercuration reduction. All right, so we start with our cyclopentene. So the first step, all right, so it's oxymercuration. So which metal do you think is involved? It's mercury. So we have mercury acetate, which looks like that. So we're going to react mercury acetate and water with our pi bond. And then we're going to have to draw a second step down here. So we just indicate that with numbers, right? So our first step is going to be our mercury and our water. And then the second step, we will use NaBH4. So NaBH4 is sodium borohydride. And so this second part is essentially an example of a workup step. That gets us to the final product. All right, so the ultimate product we see from the oxymercuration, yeah. What is that? Oh, so in the, we can blow that up. So this is mercury OAC2, mercury acetate. And so what that looks like, that is equal to Hg, OAC, OAC, and even in more detail, that is this right here. But it's not particularly important, so I was just using O-acetate. You can use O-acetate, that's perfectly fine. So just OAC, it works. Okay, so that's mercury acetate. So the product we end up with when we do this reaction is essentially going to end up as the Markovnikov addition of water to our double bond, which we've already been able to do once, right? When we did the catalytic acid along with water, we found that we got the Markovnikov addition of water. But what we're going to see is there are some advantages to using mercury over our catalyzed acid version of that reaction. All right, so even though it's not a halogen, we're going to go through a very similar type mechanism, which means we're going to go through a 3-membered ring. So we've got mercury. We're just going to use OAC. We don't care about what the OACs really look like. So we've got mercury acetate. And so since we're still doing a type 2 mechanism, how do you think we start our arrow drawing? Where do you think we start them? At electrons. And again, it's going to be electrons at the pi bond. So where are we going to draw that arrow to, do you think? It's going to be the mercury. The mercury is going to be our electrophile. So we have 3 arrows every time we've been doing these type 2 mechanisms, and we're still going to have 3 arrows. So we draw our pi bond going to our mercury. We're going to lose one of these O-acetates like this, so we'll just kick that right off. And so what's that lone pair of the mercury going to do, you think? It's going to be drawn back to our pi bond, and so we're going to end up again with a 3-membered ring. It's just now we're not using a 3-membered ring with halogens. It's going to be mercury in its place. All right, so the mercury, when it's on a 3-membered ring with the pi bond, or what was the pi bond, is that going to have to be on the same side, or can it be on opposite sides? Just like with our haloniums, it's either going to have to be 2 new wedges or 2 new dashes, and so we'll show it from the front. So we push our methyl back. so what we end up is a structure with a structure that looks very similar to our halonium intermediates before. It's just now we've got a mercurio acetate with the positive charge instead of just a bromide or a chloride. All right, so we've still got water in solution. That was part of our reactants. And so what do you think is going to happen at this point? Can water be nucleophilic? Do we have a three-membered ring that would probably like to be opened up? Yeah, we absolutely do, and so we're going to just go through the same exact steps that we've been doing all along. So we'll start our arrows at the electrons of the oxygen. And we'll approach this carbon right here. The top carbon, because it's a tertiary carbon, has a little more partial positive charge. And so the bond between the carbon and the mercury is going to break to open up that three-membered ring. Remind ourselves that this intermediate is plus the enantiomer. And so what we end up with is, let's see, all right, so our water, for the structure drawn, is it going to approach from the front face or the back face? It has to approach from the back face, which means it's going to end up as a dash. We've still got 2 protons on our oxygen, so we've more or less transferred our positive charge from the mercury to the oxygen. Our methyl has been pushed forward. And then the mercury, which is still connected to the bottom carbon, is that going to be a wedge or a dash? It's still a wedge. We haven't done any chemistry there, and so we've still got a big wedge right there. All right, mercury acetate. So we want to get to a neutral product, and so again, we're going to want to go through a deprotonation step. So we use a generic base to deprotonate one of the protons. And ultimately what we end up with is a new OH group on the back face. But we're kind of stuck because we've got mercury clinging to the front face of our ring. Now, when I sent out that homework and I had lots of examples of drugs, how many mercuries did you see hanging off of those molecules? There were no mercuries hanging off of those molecules. And in fact, we're not typically trying to make things with mercuries connected. However, what we've got is a stable intermediate. And so this is a molecule that you can absolutely recover and have it in a flask and do some analysis on it. So it is a stable intermediate, but it's not ultimately our end goal. What we want to do is just have added the hydroxyl group. Basically, have an OH there, but just a hydrogen there. And so what we have to do is then our workup step. So that's where our sodium borohydride comes into play. So sodium borohydride basically acts as a hydride source. So that's going to be an H- source. So we don't worry about the mechanism. All we need to remember is that essentially we're going to swap out our mercury for just a hydrogen, right? And so what we end up with is our final product will be our hydroxyl group on a dash, our methyl group on a wedge. So our new hydrogen on a wedge, and there's still a hydrogen there that was implied on a dash. And so you can see that what we've done in our workup step is we've swapped out that mercury for a hydrogen. So that's much more likely to be an intended product that we're trying to make, and so that's ultimately the end goal, is we're always going to hit it with the sodium borohydride to wipe out all that mercury. Okay. So, we can already make this product. We know that if we took this alkene right here and reacted it with H2O and catalytic acid of some kind, would we end up with the Markovnikov addition of water to our alkene? Yeah, that was the second reaction we learned, is that we could go from basically this alkene here and use water and catalytic acid to form this. So why would we use mercury in place of our water and catalytic acid? All right, so what kind of mechanism does this bottom reaction go through? Is it a halonium? No, it's a carbocation, right? We've already talked about how carbocation reactions have some weaknesses. So let's ask ourselves, why use mercury acetate when we could use H2O and catalytic acid? And so first and foremost, does a carbocation mechanism give us any stereoselectivity? if you look back at your table, we wrote a big none under stereoselectivity. And so by using mercury acetate, we get anti-stereoselectivity. So we could say that anti-stereoselectivity provides fewer products. And it's always better if we can end up with fewer products because it's going to be that much easier to get those molecules pure. And then number 2, what can only happen if we go through carbocation mechanisms? 1,2 hydride or 1,2 alkyl shifts, right? We require a carbocation to ever see that. So by going through the oxymercuration reaction, we can also avoid any 1,2 shifts of any kind. And so it's typically always going to be ideal to go through the oxymercuration reaction instead of the water and catalyzed strong acid reaction. Peter?
Why do you want to avoid 1,2 shifts?
Well, if you go through 1,2 shifts, you're opening up different pathways. You can end up with lots of different products. And so when you're really doing this thing in the lab, you know, the ideal reaction is a reaction where you treat it to your reagents and you end up with one product. And you don't have to worry about purification. That's just the product you have. But if 1,2 hydride shifts and 1,2 alkyl shifts are possible, you end up with the possibility of forming 4, 6, 8 different products. And so those are ultimately going to be very similar products. They differ in stereochemistry or minor regiochemistry. And so they're very difficult to separate. And so you always want to try to form as few products as possible. So that's why. All right, so let's add that to our table. So that's reaction number 5, is that right? Okay. All right, so our electrophile, what do we end up in our product as having added as the electrophile? What adds to our secondary carbon? It's a hydrogen in the end product, right? And so that's what we'll show. We'll say we end up in our product with the hydrogen being the electrophile. What's the nucleophile? What adds to the tertiary carbon? It's OH. And so the reagents we want to use, they're always 2-step reactions. So you're going to hit it with mercury acetate and H2O. And then you're going to hit it with the workup step of sodium borohydride. The regioselectivity of this reaction, what is it? Yeah, it's Markovnikov because we've added our electrophile to the less substituted carbon, or the carbon with more hydrogens. So we have Markovnikov regioselectivity. What about stereoselectivity? Yeah, so when we look at our water here and our mercury acetate, are those syn or anti? Those are anti. Does that make sense for having gone through a type 2 mechanism? Yeah, absolutely. And so that's what we would expect to see. We'd expect to see the anti-product, and so we'll call that anti. And so again, this is just going to be an X plus type mechanism, so a Halonian mechanism. Yeah?
Is the mercury acetate like the only molecule that this happens in?
It's the one we're going to talk about in here. Certainly you could use different kinds of mercury with different things coming off of it, but we're just going to keep the mercury acetate. Acetate is a really common ligand for these sorts of things. All right. So that's it for type 2 mechanisms. So we're just going to head to type 3 mechanisms and learn some more reactions. And then ideally we'll be done by the end of class on Wednesday, and we can spend Friday looking at some nuances of things and kind of preparing for the exam in a week from now. So this is Roman numeral number 7. And so we will label it mechanism type 3. And so we've had carbocation, we've had halonium, and so now we're going to have concerted, which we might just abbreviate as CONC. Does anyone have any idea what concerted means as it pertains to organic reactions? All right, so concerted, essentially what it's going to mean, and it's pretty straightforward. It means that the electrophile and the nucleophile will add to the alkene at the same time. Have we seen that yet? No, every time we've been adding these two things to our pi bond, we've been adding the electrophile first, going through some intermediate, and then adding our nucleophile. But now what we're going to see are these concerted mechanisms that basically go through one step. All right, so let's talk about an alkene for a second. All right, so this structure that I've drawn, is this the only resonance structure that we can draw for it using the rules that we've talked about? You can just nod or shake your head. Or just look at me. That's fine too. All right, so what if I told you that we could try to draw this resonance structure? And so we'd end up with a lone pair on that carbon, so that's negatively charged, and then a positive charge there on that bottom. All right, is that okay according to all the rules we've learned? We have an open shell atom, but what have we said about open shell carbons? They're perfectly allowed, and we've seen why, because they exist. They're really important. So we do have a valid resonance structure, and so if we can draw our electrons from the pi bond going up, where else can we draw them? Going down, right? And so let's do that. We'll end up with a third structure. And so in that case, we have a positive charge on the top, negative charge on the bottom. All right, and so let's just use our, let's go back a month and let's just rank the structure. So what's the most stable structure? It's definitely the middle one, because the middle one's closed shell, right? And so that's why we draw it that way. We're going to see a contribution of the middle one by like, it's going to be like 99.9%. Certainly this is going to be by far the more favorable structure, but we're also going to see contributions from the blue structure as well as the red structure. And so what's going to make more of a contribution? Is it going to be the blue structure or the red structure? Why blue? Yeah, and so essentially what we can do is we can compare those charges. So here, we've got a positive charge on a tertiary carbon. Here, we've got a positive charge on a secondary carbon. And so we know that a carbocation that's tertiary is more stable. So we would end up ranking this number 2, and ultimately this one number 3. Okay, so what that means is when we look at our structure that we've drawn right here, yeah, 2 and 3 are going to make very, very minor contributions. And so the real nature will be a hybrid of these 3, but it's basically going to be this. But we do have minor nuances in the electronic nature of that alkene. And so what that means is we can draw partial charges for this top carbon and this bottom carbon. All right, so knowing what we know about the rankings here, this top carbon, do you think it would get a partial positive or a partial negative? Yeah, it's going to be a partial positive. And again, the reason for that is just because we have a resonance structure here that is more highly favored than this resonance structure here. And so if we have a partial positive charge on top, we're also going to have a partial negative charge on bottom. All right, so let's hit this thing with an electrophile-nucleophile combo. And so if we have an electrophile and a nucleophile, and we want to draw partial charges on these two things, is an electrophile going to have a partial positive charge or a partial negative charge? Partial positive, right? It's an electrophile. It loves electrons, and that's because it itself is a little bit positively charged, right? That's why we always attack the electrophile with our electrons from the double bond. It's because there's a little bit of partial positive charge on it. And so, likewise, our nucleophile, for the same reasons, has a partial negative charge. All right, so we should see a little bit of a pattern emerged. I've drawn this electrophile-nucleophile combo in a way such that the top carbon here, which has a partial positive charge, is right next to this nucleophile with a partial negative charge, and then vice versa. This partially negatively charged carbon on the bottom is aligned with the electrophile, which is partially positive, right? And so what we've done is we've aligned our partial charges. And so when we start our reaction, where do you think we start our arrow? Double bond of the alkene every time. Where are we going to draw it? Is it going to be to the electrophile or the nucleophile? It's going to be the electrophile, like every other time. What we're going to do a little bit differently, in addition to this arrow, is this bond between the nucleophile and the electrophile, it's just going to snap right over to the alkene. And so in showing this, where are we going to start our arrow? At the electrons, at that sigma bond. We'll just start it there, and we'll draw it right into the carbon. such that now for the first time we're seeing that we can add our nucleophile and our electrophile at the exact same time. We're not going through an intermediate. These things are just going to add in one step. And so what we end up with, let's actually, all right, so when we add this nucleophile and electrophile combo, do you think that they're going to have to come from the same face of the double bond? Well, let's draw it on end. Let's see what it would look like. So we've got our double bond here. We'll say we have p orbitals straight up and down. So let's make this right one a primary carbon. And so we'll make the left one a tertiary carbon. So we need a methyl here and a methyl here. And so we've got two lobes of our pi bond, or two lobes of our p orbitals, right? We've got this area of electron density on top and area of electron density on bottom. It's ultimately going to be those lobes that are reacting with our electrophile-nucleophile combo. Okay, so we have our electrophile. So remember, we have our partial positive on the tertiary with our partial, it's a lot of partials. Partial negative on the primary. We want to put partial positive here. And partial negative here. All right, so do we have that aligned correctly? Yeah, we've got our negative carbon next to our positive electrophile. And so what we'll show is that this is all going to happen at one point, where our electron density is going to come from the top face. If it's going to happen at the same time, ultimately this nucleophile is going to interact with this carbon. Is it ever going to be able to interact with the bottom side at the same time? No, definitely not. It's really, really close to the top face. And so what we find is that these things are going to add to the same side of the double bond every time. So ultimately, our sigma bond between the nucleophile and the electrophile will snap in to the top face of that carbon. So what that means is that, let's say over here in our picture, let's say we're going to use our nucleophile and electrophile approaching from the front face. That's going to push our methyl back on a dash. We'll draw our nucleophile on a wedge. And then our electrophile, is that going to be a wedge or a dash? It has to come from the same side, right? For exactly this reason right here. And so if it's going to come from the same side in this one-step reaction, we're also going to have that on a wedge. We'll have plus an enantiomer. And so is this going to be an example of an anti or a syn addition? Syn. Yeah, this is syn. We're adding our electrophile and our nucleophile to the same side. So when we talk about stereochemistry, we've got a syn addition. When we talk about regiochemistry, what would you call it? Are we still snapping our electrophile to our less substituted carbon? Yeah, in this general case we are. And so yet again, we're going to find that we have Markovnikov addition. But I will add that we're going to see one example that is anti-Markovnikov. All the other ones are, in fact, Markovnikov. So we'll add, we'll say that BH3 addition is anti-Markovnikov. That's the only exception. All right, so we'll just look at these reactions on Wednesday. I've got an office hour today from 2:30 to 3:30. I'll have all the homeworks out and up to date as of this afternoon. And so, yeah, I'll see you either at office hour or tomorrow. We also have an office hour. I want to say that's 10:30 to 11:30. And so otherwise, I'll see you on Wednesday. I think the room number is 2018. Do you know where the reading room is? At the end of the hallway from the undergrad.
Hey, you drew all these notes from last Friday.
Oh, yeah, I do that sometimes. I'll just switch it over. Yeah.